Let us now move to uniform reliable broadcast. And remember, uniform reliable broadcast has the agreement property that if a process delivers, dead or alive, all correct processes will deliver the message. So a question about uniformity now: is the proposed algorithm that we just described for reliable broadcast uniform? Observe that uniform necessitates that if a failed process delivers a message M, then every correct process delivers the message M. So the answer is no. And here is a possible execution where the sender immediately RB delivers, as you can see here, and of course it will do a BEP broadcast, but then it crashes. In this case, it is possible that this process P is the only one that delivered the message, because there is no guarantee that a BEP broadcast will be delivered by all correct processes, because the sender has already crashed. So here you can see here, I just draw it in a line. The process do an RB broadcast, and then it does RB deliver of M, then it does BEP broadcast, and then it crashes. By the BEP validity, there is no guarantee that this BEP broadcast is delivered to all correct processes. So we need another algorithm to guarantee uniformity. The necessary condition for uniform delivery is that let us make sure that all correct processes will get the message first before we deliver our message. So this leads us to the next question, which is, how do we know that correct processes got the message? So the way to do it is to make sure that the message is not delivered until we are sure that all correct processes got the message. So messages will be in a pending state, actually stored in a pending variable, until all correct processes got it. And what we do then is we collect acknowledgement from processes that got the message. And we do this by, at each process PI, we have a vector called ACK, indexed by every message M, so that this vector will contain the set of processes that acknowledge the message. And then we deliver the message once all correct processes have acknowledged. As you can see from this method, we can only do this by using a perfect failure detector that track which processes are correct and which are faulty. So we are using a perfect failure detector, which means that we are in the fail-stop model, the synchronous system. And here is the function canDeliver. CanDelivers will return true if the set of correct processes is included in the set of processes that acknowledge the message. This is what it says. So the algorithm that we are going to describe now works only for the synchronous case where we can use a perfect failure detector P. So let us look to the algorithm in detail. When we get a uniform broadcast request, what do? We store the message M in a variable that contains all pending messages that are not delivered yet. So this is, remember, the sent messages. And then we trigger a best ever broadcast to all processes in the system. A BEP broadcast will cause a delivery event at each process or at each correct process. So when we get a delivery event for a message M from source SM, we add this process PI, the sender, to the set of processes that have acknowledged the message. And if the message was not already in the pending list, then we add it to the pending list or the pending set, and then we trigger a web broadcast to all processes. So that is fine. Then we have the following condition where we can deliver a message. So if there is a message in the pending set, the message M, and if can deliver M is true, it means we got acknowledgement for all correct processes, and M is not already delivered, then we add M to the delivered set, and then we trigger a delivery of the message. So this is the algorithm for uniform eager broadcast in the fail-stop model. Let us see an example where we have no failure, just to understand the concept. So process P1 does a uniform broadcast of message M. This will lead to a web broadcast from P1. So the web broadcast goes to P2 here and P3 here. And whenever a process like P2 gets the web broadcast, it does itself a web broadcast. So it will send a web broadcast to everybody. So the message will be delivered at all other processes. So it will be delivered here, and it will be delivered here. Now, when P3 receives the web broadcast, and it does the delivery, it also performs the web broadcast. And in this case, it will web broadcast to all other processes like here and here. And it will web broadcast to itself also here. So this will be a delivery of its web broadcast. Now, if we look to any process, for example, let us look to P1. So P1 will uniformly deliver the message only if it got a web delivery of that message from all processes, including itself. And here it got from itself, here it got from P2, and here it got from P3. So P1, P2, P3, and now it can deliver. Now let us look to the correctness of the uniform reliable broadcast algorithm. No creation is guaranteed by the best ever broadcast, no creation. No duplication is guaranteed by using the delivered set that we have seen in the algorithm. And now before we prove the validity property of the uniform broadcast and the uniform agreement, we first prove a lemma. And this lemma says if a correct process PI bib delivers M, then PI will eventually uniformly delivers M. Again, if a correct process PI bib delivers, then eventually PI will uniform delivers. So let us see the proof of this lemma. So we assume that PI is a correct process. So what a correct process does? A correct process PI web broadcast M as soon as it gets M. So it web broadcast M. And it is a correct process. So by the best effort broadcast validity property, which says if a correct process broadcasts a message, all correct processes will deliver the message. So every correct process gets M. And whenever a correct process gets M, it will also broadcast M. Which would mean that PI will get a best effort delivery from every correct process. And now, by the completeness property of the failure detector, it will not wait for dead nodes forever or dead processes forever. So eventually then the can deliver condition will become true. Can deliver is saying if I got acknowledgement from all correct processes. So this condition will become true, and in that case PI will deliver the message M. So now we know again this thing. We remember if a correct process BEP delivers, a correct process will uniformly deliver. Now let us look to validity. And validity says if the sender is correct, then the sender will deliver the message. So if the sender is correct and the sender does, as you can see, a best effort broadcast, then the sender by the best effort broadcast will deliver the message M. And by our lemma, if a process BEP delivers, it will uniformly deliver, then this sender will also uniformly delivers. Now let us look to the uniform agreement property, which says if a process delivers, all correct processes will deliver. So let's assume that some correct process which has possibly failed uniformly delivers the message M. And what that mean? It means that the can deliver M was true, and can deliver M is true when it got acknowledgement from that message from all correct processes. And how it gets the acknowledgement from correct processes? It gets it by the correct processes performing a BEP broadcast. So now, by the accuracy of P, you have actually detected that all correct processes best effort broadcasted the message. So it means that every correct process has BEP broadcast M. And by our lemma, if a correct process that best effort delivered M will uniformly deliver M. So let us try first to understand why we need the accuracy here. So let us look to a process P1. Process P1 did a uniform broadcast, which means that P1 did a best effort broadcast to a set of processes here. Here we are in a situation which can deliver is true. But P1 suspected falsely that P2 has failed. In this case, P1 uniform deliver and then crashed. Now because P1 has suspected falsely P2, there is no guarantee that the BEP broadcast that has been issued by P1 will be delivered to P2. And therefore, there is no guarantee that P2 will eventually do itself a best effort broadcast and then uniformly deliver. So it is possible that some process, in this case P2, will not best effort deliver the message, and therefore there is no guarantee that that process P2 will uniform deliver the message.